66 million years ago, on an ordinary spring morning in what would one day be called the Cretaceous period, a mountain-sized celestial projectile was hurtling toward Earth at 20 kilometers per second. It had traveled for millions of years through the cold silence of space, its trajectory shaped by an almost infinite chain of gravitational interactions, the pull of Jupiter, the nudge of passing comets, the slow wobble of its own spin. None of that history mattered anymore. What mattered was that in approximately 4 hours, this 10-kilometer sphere of carbonite and iron would strike the shallow seas off what we now call the Yucatan Peninsula, and it would change everything. The impact released the energy of 100 million atomic detonations. It vaporized billions of tons of rock, sulfur, and seawater, launching a cloud of debris into the stratosphere that would circle the globe within hours. Wildfires swept across continents. Tsunamis, hundreds of meters high, crashed against coastlines, thousands of kilometers from the impact site. And then came the darkness, a years-long twilight as the sun vanished behind a shroud of dust and sulfur aerosols, dropping global temperatures by nearly 30 degrees Celsius. The plants died first, unable to photosynthesize. Then the herbivores that depended on them. Then the predators that depended on the herbivores. Within a geological instant, 3/4 of all species on Earth were gone, including every dinosaur larger than a house cat. That is what happened. That is the history written in stone, in the thin layer of the iridium-laced boundary layer that marks the boundary between the Mesozoic and Cenozoic eras. In the 200-kilometer scar buried beneath the sediments of the Yucatan. But tonight, we are going to imagine a different history. We are going to ask what would have happened if that rock, that mountain falling from the sky, had missed. It nearly did, you know, or rather, it nearly could have. The specific trajectory of any asteroid depends on countless variables stretching back billions of years, and a change in any one of them would have produced a different outcome. Some researchers have calculated that if the Chicxulub impactor had arrived just minutes earlier or later, it would have struck deep ocean rather than shallow coastal waters, less vaporized rock, less sulfur in the stratosphere, a regional catastrophe rather than a global extinction. The dinosaurs would have woken up the next morning to a world shaken but not destroyed. And they would have continued doing what they had been doing for the previous 165 million years, dominating every terrestrial ecosystem on the planet. So, before you get comfortable, take a moment to like the video and subscribe, but only if you genuinely enjoy what I do here, and let me know in the comments where you're tuning in from. I'm always curious to see how far these stories travel. Now dim the lights if you haven't already. Take a deep breath and let the modern world fade away. Listen for the sound of wind through Cretaceous ferns, the rustle of a world preparing to continue rather than end. This is the story of 66 million years that never happened, and we're going to walk through every step of it together. The discovery that an asteroid killed the dinosaurs is itself a remarkable story, and it's worth telling briefly because it shows how science works, how a radical idea, dismissed at first as fantasy, can become accepted fact when the evidence accumulates. In 1980, a physicist named Luis Alvarez and his geologist son, Walter, were studying rock formations near Gubbio, Italy, examining the thin layer of clay that marks the Cretaceous-Paleogene boundary. They found something strange: iridium, and lots of it, 30 times the normal concentration. Iridium is rare on Earth's surface because most of it sank into the planet's core billions of years ago, when the Earth was still molten. But it's common in asteroids. The Alvarez team proposed that a massive impact had occurred at exactly the moment the dinosaurs disappeared, and they predicted that somewhere on Earth there should be a crater to prove it. The scientific community was skeptical. Many geologists preferred volcanic explanations. The Deccan Traps in India had been erupting for millions of years. Around the same time, pouring enough lava to cover half of modern India in basalt, kilometers thick. Surely that was enough to explain a mass extinction. But the Alvarezes kept gathering evidence, and other researchers joined the hunt for the crater. In 1978, a geophysicist named Glenn Penfield had noticed something odd while surveying for oil in the Yucatan, a vast circular structure buried beneath the sediments, visible only in gravity and magnetic anomaly maps. He didn't know what it was, but he suspected it might be an impact crater. It took another decade for the connection to be made, for samples from Mexican oil wells to be tested and found to contain shocked quartz and tektites, minerals that form only under the pressures of an asteroid impact. By 1990, the case was closed. The crater was real, it was exactly the right age, and it was exactly the right size to have caused the extinction. But here is the thing about asteroid impacts, the thing that makes our thought experiment possible. They are not inevitable, they are not destiny. They are contingency, pure and simple, the result of orbital mechanics and gravitational perturbations playing out over timescales so vast that the outcome might as well be random. The Chicxulub impactor could have arrived a few minutes earlier and splashed into deep water. It could have arrived a few hours later and struck the middle of the Pacific. It could have missed Earth entirely, sailing past our planet and continuing on into the outer solar system, never to return. In any of those scenarios, the dinosaurs would have survived, not because they were destined to survive, but because the particular event that killed them simply wouldn't have occurred. Our story begins in that alternative moment. The asteroid screams through Earth's atmosphere, carving a white-hot trail across the sky, visible from 1,000 kilometers away. It strikes the Pacific Ocean 2,000 kilometers from the nearest coastline, generating tsunamis that devastate coastal regions across the Americas and Asia. Millions of creatures die, ecosystems are disrupted for decades, but the sulfur stays in the ocean. The dust settles within months rather than years. The sun keeps shining, the plants keep growing, and the dinosaurs, the tyrannosaurs and triceratops, the hadrosaurs and ankylosaurs, the tiny feathered maniraptorans darting through the underbrush, continue their ancient reign as if nothing had happened. Because for them, nothing significant has happened. They have survived worse. They have survived the volcanic winters of the Deccan eruptions, the gradual cooling of the late Cretaceous, the shifting continents and changing sea levels that have been reshaping their world for millions of years. They are the most successful group of large land animals the planet has ever produced, and they show no signs of decline. Their diversity is at its peak. Their body sizes range from avian-scale bug hunters to 40-ton herbivores. They occupy every ecological niche, from Arctic forests to tropical swamps. They have been doing this for 165 million years, and there is no biological reason why they cannot continue for 165 million more. The world belongs to the dinosaurs, and now, for the first time in Earth's history, we are going to see what they would have done with it. To understand what might have been, we first need to understand what was. We need to step back from the alternative history we're constructing and look clearly at the world the dinosaurs would have continued to inherit, not the simplified version from children's books, not the cinematic monster movie landscape, but the real late Cretaceous Earth in all its complexity and strangeness. Forget the barren volcanic hellscapes that sometimes populate the popular imagination. The world of 66 million years ago was a world of extraordinary abundance, warmer and wetter than anything we know today. There were no ice caps at the poles. Sea levels stood perhaps 170 meters higher than our modern oceans, drowning coastal plains and splitting continents with shallow inland seas. North America wasn't one landmass, but two, divided by a warm waterway called the Western Interior Seaway that stretched from the Gulf of Mexico all the way to the Arctic Ocean. India was an island, drifting northward on its inevitable collision course with Asia. Australia still clung to Antarctica, and both were green with temperate forests. The air itself was different. Carbon dioxide levels perhaps 4 times what they are today. Oxygen slightly higher. The greenhouse effect, keeping the planet warm from pole to pole. Crocodilians lived above the Arctic Circle. Forests grew where Antarctic ice sheets now grind against bedrock. There were no ice caps at the poles. Sea levels stood perhaps 170 meters higher than our modern oceans, drowning coastal plains and splitting continents with shallow inland seas. North America wasn't one landmass, but two, divided by a warm waterway called the Western Interior Seaway that stretched from the Gulf of Mexico all the way to the Arctic Ocean. India was an island, drifting northward on its inevitable collision course with Asia. Australia still clung to Antarctica, and both were green with temperate forests. The air itself was different. Carbon dioxide levels, perhaps 4 times what they are today, oxygen slightly higher, the greenhouse effect keeping the planet warm from pole to pole. Crocodilians lived above the Arctic Circle. Forests grew where Antarctic ice sheets now grind against bedrock. And everywhere, in almost every terrestrial niche you could imagine, there were dinosaurs. The best window we have into this vanished world is a place called the Hell Creek Formation, a layer of rock stretching across Montana, the Dakotas, and Wyoming that preserves the last 3 million years of the Cretaceous in exquisite detail. When paleontologists dig there, they don't just find isolated bones, they find an entire community of life frozen in stone, a complete ecosystem that we can reconstruct with remarkable precision. The ruler of this world was Tyrannosaurus rex, and it's worth spending a moment really seeing this animal as it was, not as the lumbering tail dragger of old reconstructions, but as something far more terrifying and far more beautiful. 12 meters in length from nose to tail, with 9,000 kilograms of muscle and bone supported by legs shaped like those of a sprinter and intended for quick acceleration rather than steady running. With teeth the size of bananas, each serrated like a steak knife, and the ability to pierce bone as easily as you could bite through an apple, the skull was big enough to swallow a human being whole. But the most remarkable feature was the eyes. T-Rex was unique among dinosaurs, in that it had binocular vision and depth perception, thanks to its forward-facing eyes, set in a narrow front skull. A study by vision researcher Kent Stevens calculated that its visual acuity exceeded that of modern hawks, that it could spot prey from 6 kilometers away, that its ability to judge distance was among the best of any animal that has ever lived. This was not a scavenger waiting for something to die. This was the undisputed sovereign of the food chain, with the sensory equipment of a precision hunter. But T-Rex was the exception among predators, not the rule. The Hell Creek ecosystem supported a whole range of carnivores, filling different niches. Smaller tyrannosaurs that may have hunted in groups, dromaeosaurids with their famous sickle claws, and troodontids, those strange large-eyed hunters whose brains, relative to their body size, were larger than any other dinosaur group. We'll come back to the troodontids later because they matter enormously to our story. For now, just note that they existed, small, smart, watching the world with eyes that saw more than most. The herbivores were even more diverse, and among them, one animal dominated so completely that it's hard to overstate its importance: Triceratops. Paleontologist Robert Bakker once estimated that Triceratops bones make up 5/6 of all large dinosaur fossils in late Cretaceous North America. And if that number is even close to accurate, we need to fundamentally reimagine the Cretaceous landscape. Imagine the vast plains prior to European contact, when you could travel for days without seeing anything but grass and grazing animals, when bison herds stretched from horizon to horizon, and when the ground shook beneath millions of hooves. Now replace each of those bison with a 9-meter-long, 3-horned tank that weighed up to 9,000 kilograms. Its skull made up 1/3 of its body length, and its neck was protected by a frill of solid bone. Its horns were capable of goring a tyrannosaur, that was a Triceratops, which were armored like medieval knights, and the Cretaceous counterpart of the American bison. The hadrosaurids, or duck-billed dinosaurs, coexisted with Triceratops. They had incredible dental batteries, hundreds of interlocking teeth arranged in columns and continuously replaced, that allowed them to grind tough vegetation in a manner unmatched by any other dinosaur group. Ankylosaurus, the armored stronghold, was there. Its body was covered in osteoderms, which are bony plates, and its tail ended in a fused bone club that could break a predator's leg with a single blow. There was Pachycephalosaurus, with its dome of solid bone atop its skull, possibly used for headbutting contests, like modern bighorn sheep, though paleontologists still argue about this. And there were dozens of smaller species, each filling its own niche in the ecosystem. At night, tiny mammals scuttle through the leaf litter. Oviraptorosaurs tend to their nests, and small ornithopods browse in the undergrowth. Above this world flew the pterosaurs. And we need to pause here, because the pterosaurs are not dinosaurs. They're a separate lineage entirely, related but distinct, like cousins rather than siblings. Quetzalcoatlus, named after the Aztec feathered serpent god, was the largest of them. When I tell you that its wingspan reached 11 meters, I need you to really picture that wider than a small airplane and bigger than any flying animal that has ever existed before or since. Standing on all fours, it would have looked a giraffe in the eye. Yet its bones were hollow, honeycombed with air pockets, so lightweight that this creature, the size of a small aircraft, probably weighed only about 250 kilograms, less than many adult humans. It probably hunted like a giant stork, stalking across floodplains on folded wings, snatching up small dinosaurs and mammals, and fish with a beak the length of a human arm. And what about the mammals? They were there. They had been on the planet for more than 150 million years, evolving with the dinosaurs from the very beginning. However, they were tiny. The largest known Cretaceous mammal was possibly the size of a badger. The majority were about the size of mice or rats, and they hunted seeds and insects in the ecological periphery cast by the giants, while creeping through the underbrush and climbing trees at night. They were very successful at what they did. They were not failures, but what they did was stay out of the way. The niches they occupied were the niches the dinosaurs didn't want. The tiny insectivore niche, the burrowing niche, and the nocturnal niche. The ruling reptiles owned everything else. On the morning the asteroid missed, this was the world. A world of warmth and abundance, of continental drift and shallow seas, of theropod hunters and ceratopsian herds and pterosaurs soaring on thermals above it all. A world that was, if anything, at the pinnacle of its success and diversity, had been perfecting itself for more than 165 million years and showed no signs of decline. The dinosaurs weren't waiting to be replaced. They weren't biological cul-de-sacs that would eventually go extinct. They were the most successful group of large land animals the planet had ever produced, and they had every reason to expect that their reign would continue indefinitely. It almost didn't, of course. The rock from space ended everything in our timeline. But in the timeline we're exploring tonight, the rock splashed harmlessly into the Pacific, and the dinosaurs woke up the next morning to continue what they had been doing for 165 million years. The question now is, what would they have done with another 66 million years of evolution? What would they have turned into? To answer that, we need to understand something that the dinosaurs themselves couldn't have known. The world was about to change, over tens of millions of years, slowly and unavoidably, rather than abruptly or catastrophically. The warm, stable climate of the Mesozoic was ending. Antarctica would eventually become frozen due to a protracted cooling caused by the gradual drift of continents, the massive tectonic uplift, and the movement of ocean currents. New plants were evolving. Grass would proliferate worldwide and change every ecosystem they came into contact with. The asteroid could never test the dinosaurs' ability to adapt, and they were about to face challenges they had never faced in their 165 million years of evolution. Let us first examine the reasons behind the dinosaurs' initial dominance and the inability of mammals to emerge from their ecological periphery. It's not what you might think. There's a story that gets told in countless documentaries and textbooks, a comfortable narrative that explains why the world looks the way it does today. This is how it goes. Because nothing better had emerged yet, the dinosaurs, slow-moving evolutionary relics, and biological cul-de-sacs dominated. They were big and dumb, slaves to their instincts, unable to adapt to changing conditions. The asteroid's impact merely made room for Earth's legitimate heirs. The intelligent, endothermic physiology mammals had been waiting patiently in the wings for their chance to shine. Extinction was nearly a blessing, a necessary reset that made it possible for evolution to make amends. In order to comprehend what would have happened if the dinosaurs had survived, it is necessary to comprehend why this story is nearly entirely false. The dinosaurs were not failures waiting to be replaced. They were an evolutionary triumph of staggering proportions, arguably the most successful group of large land animals the planet has ever produced. For more than 165 million years, they dominated terrestrial ecosystems. For a moment, try to visualize that number. Humans with modern anatomy have probably been around for 300,000 years. The entire Homo genus, including all of our extinct relatives, may have existed for 2.5 million years. That is 66 times longer than the dinosaurs' reign. They evolved into thousands of species, filled every conceivable ecological niche, from tiny insectivores to 40-ton browsers, spread across every continent, adapted to every climate, from tropical rainforests to polar winters, and they showed absolutely no signs of decline in the millions of years before the asteroid struck. If anything, their diversity was increasing. Dinosaur senescence did not occur during the late Cretaceous. It was the reptilian zenith. Why, then, did mammals remain small? They had lived alongside dinosaurs for 150 million years, so why hadn't they produced anything bigger than a badger? The conventional response is straightforward. The dinosaurs were suppressing them. The big niches were occupied by big dinosaurs, and the mammals simply couldn't compete. The giants were unable to follow them, so they were driven into the outskirts, into the night, and into burrows and treetops. Mammals would proliferate into all that newly created ecological space if the dinosaurs were eliminated. Although there is some intuitive appeal to this explanation, new research indicates that it may be backward and at best incomplete. In order to determine where each lineage was reaching ecological limits, a 2021 study from Oxford and Birmingham universities compared the evolutionary constraints on various mammal groups before and after the KPG extinction, using advanced statistical techniques. They discovered something unexpected. Dinosaurs weren't the main rivals of the ancestors of modern placentals and marsupials, the groups that would eventually give rise to everything from whales to elephants to humans. They were being outcompeted by other mammals. The Mesozoic wasn't just home to the tiny shrew-like creatures we usually imagine when we think of early mammals. It was home to an astounding variety of mammalian lineages, the majority of which are extinct today. Eutriconodonts, dryostoids, gondwanathares, and multituberculates. These animals had already claimed many of the small to medium body size niches. Some were gliders, some were swimmers, some were burrowers, some had teeth specialized for cracking hard foods, others for slicing meat, others for grinding plants. Faraway dinosaurian giants weren't holding back the ancestors of modern mammals. Other mammals that were merely more suited to Mesozoic conditions were outcompeting them, including their own close relatives. Consider the implications for our alternate timeline. Yes, the dinosaurs persisted when the asteroid didn't hit, but so did these other groups of mammals. The multituberculates would have continued to compete with rodent ancestors if they had survived the extinction in our timeline and continued to exist for an additional 30 million years before eventually going extinct. In the southern hemisphere, the Gondwana would have continued to occupy the niches that marsupials might have otherwise occupied. There would not have been a level playing field. For 150 million years, the mammals that eventually gave rise to elephants, primates, and humans would have been stuck in the same competitive squeeze, pressed from the sides by their own kind, and from above by dinosaurs. But let's delve deeper and consider why the dinosaurs were so adept at being big in the first place. The answer reveals something essential about the limitations that our alternate past would have faced. Mammals just cannot match the respiratory system of dinosaurs. They breathed using a system of unidirectional airflow through stiff lungs that were augmented by air sacs that extended throughout their bodies, even into their bones, just like modern birds, which are, after all, living dinosaurs. When a mammal breathes, air enters the lungs and exits in the same manner, combining stale, carbon dioxide-rich air with fresh, oxygen-rich air. It's inefficient. A dinosaur's breath extracted significantly more oxygen because the air only moved in one direction and passed over the gas exchange surfaces repeatedly. This explains why mammals at base camp gasped for air, while birds were able to soar over Mount Everest. This explains why the largest land mammals have never weighed more than 20 tons, but sauropods can reach 50 tons. The dinosaurs were physiologically better at being large than simply filling the large body niches. In addition, their skeletons were lighter than those of any mammal because of their hollow bones, which were pneumatized with air pockets attached to their respiratory system. They grew more quickly, reaching adult size in years, as opposed to the decades needed by mammals of comparable size. They did not have to carry their developing young inside their bodies because they laid eggs. A pregnant sauropod would have been a biomechanical impossibility, but an egg-laying one could produce dozens of offspring per year. Their entire biology was tailored to the ecological functions they had been performing for 165 million years. A mammal trying to evolve into a large herbivore in this world would have faced competitors who could breathe more efficiently, grow faster, reproduce more quickly, and carry less weight per unit of structural strength. Mammals were just attempting to compete in a game where the rules favored a different body plan. It's not that they were a less good species overall. If you place mammals in the ecological void created by the KPG extinction and leave them alone for 66 million years, they will produce giant ground sloths, elephants, and whales. Keep the dinosaurs around, and the mammals will remain what they had always been: small, nocturnal, ecologically marginal. This is the world our alternative timeline inherits. A world where dinosaurs are the unchallenged masters of every terrestrial ecosystem, where their biological advantages make them practically unassailable in the niches they occupy, and where mammals are forced into their traditional roles by competitive pressure from multiple directions, rather than a world where dinosaurs are delicate relics, barely hanging on. The dinosaurs didn't win their throne by accident or by default. They won it by being extraordinarily good at what they did, and nothing about the asteroid's near miss would have changed that. This is where the narrative becomes intriguing, though. A steady, warm climate that had endured throughout the Mesozoic era served as the basis for the dominance of the dinosaurs. The Earth had been a greenhouse for 165 million years, with little seasonal variation, humidity, forests, and warmth from pole to pole. The dinosaurs were beautifully adapted to this world, where they had evolved. They had never encountered the Great Glacial Epoch, seen a grassland, or encountered the kind of extreme climate fluctuations that would define the upcoming Cenozoic. The world was about to change in ways the dinosaurs had never encountered. The continents were drifting into new configurations, opening ocean gateways that would alter circulation patterns around the globe. Antarctica was separating from South America, and within a few million years, a cold current would begin circling the southern pole, isolating an entire continent and seeding it with ice. The Himalayas were about to rise as India crashed into Asia, their weathering rocks drawing carbon dioxide from the atmosphere and cooling the planet. Grasslands were about to spread across continents, creating entirely new ecosystems with entirely new selective pressures. The dinosaurs had proven themselves masters of the Mesozoic world. The question that our alternative history must answer is whether they could have mastered the Cenozoic world too. A world colder, drier, more seasonal, more variable than anything they had experienced in their long evolutionary history. A world that would have tested their adaptability in ways the asteroid never did. that would have demanded innovations their lineage had never been required to produce. They had 66 million years to find out. Let's see what they might have done with them. 10 million years have passed since the asteroid missed, and if you could somehow travel back to this world, you might not notice anything different at first. The continents haven't moved much. Continental drift operates on timescales of centimeters per year, and 10 million years isn't enough to rearrange geography in any dramatic way. The climate is still warm, still humid, still tropical even at high latitudes. The forests still stretch from pole to pole, dense and green and dripping with moisture. It looks at first glance like the Cretaceous world we left behind. But evolution doesn't stand still, even when the world seems unchanged. 10 million years is an enormous span of time, longer than the entire existence of the genus Homo, longer than the time separating the first stone tools from the smartphone in your pocket. Species don't remain static over such periods. They drift, they adapt, they specialize, they diverge. The dinosaurs of 10 million years post-asteroid would not be identical to the dinosaurs of the Cretaceous, even if their world remained superficially the same. The most significant change in this period wouldn't have been the dinosaurs themselves, but the plants they depended on. The flowering plants, angiosperms, had been spreading throughout the Cretaceous, diversifying and competing with the older conifers and ferns that had dominated Mesozoic forests. Without the catastrophic disruption of the extinction event, this process would have continued unabated. The angiosperms had advantages that made their eventual dominance almost inevitable. They could reproduce faster, evolve more quickly, form more intimate relationships with pollinators and seed dispersers. By 10 million years after our divergence point, they would have conquered most of the world's forests, and many of them would have been bearing fruit. Fruit is one of evolution's great innovations, a bribe offered by plants to animals. Eat this sweet, nutritious flesh, and carry my seeds somewhere else in your gut. Deposit them with a pile of fertilizer. Give them a head start in life. It's a strategy that works spectacularly well, which is why it evolved independently in so many plant lineages. In our timeline, the explosion of fruit-bearing plants in the early Cenozoic helped drive the evolution of fruit-eating mammals, the primates, who would eventually give rise to us. In our alternative timeline, the same opportunity would have been available, but the animals best positioned to exploit it wouldn't have been mammals. They would have been dinosaurs. The Maniraptor and theropods, the lineage that includes dromaeosaurids, troodontids, oviraptorosaurs, and the ancestors of modern birds, were already showing adaptations that would have served them well in fruit-rich forests. They had prehensile digits capable of manipulating objects and gripping branches. Many of them had forward-facing eyes that provided binocular vision, useful for judging distances when reaching for food or leaping between trees. They were small enough to climb, light enough to venture onto branches that would have snapped under the weight of a larger dinosaur. And some of them, the oviraptorosaurs in particular, had already evolved toothless beaks that might have been well suited for processing fruit and seeds. Picture a descendant of this lineage 10 million years into our alternative timeline. It's small, perhaps the size of a modern howler monkey, covered in a coat of colorful feathers that serve both for insulation and display. Its hands retain the 3 clawed fingers of its theropod ancestors, but they've become more dexterous, more capable of fine manipulation. Its beak has evolved a slight hook at the tip, useful for tearing open tough-skinned fruits. It lives in the canopy of the flowering forests, leaping from branch to branch, feeding on the bounty that the angiosperms provide. This creature is speculation, of course. We cannot know exactly what forms evolution would have produced in an alternative timeline, but it's speculation grounded in real evolutionary trends, in adaptations that were already present in Cretaceous maniraptorans, in ecological opportunities that would genuinely have existed. The flowering forests would have rewarded any lineage capable of exploiting them, and the small maniraptoran theropods were better positioned to do so than any mammal of the period. But not all the changes would have been in the canopy. Down on the forest floor, the great herbivorous dynasties of the Cretaceous would have been continuing their own evolution, responding to the changing composition of the plant communities they depended on. The hadrosaurids, the duck-billed dinosaurs, had evolved the most sophisticated plant processing equipment of any dinosaur lineage. Dental batteries containing hundreds of interlocking teeth, constantly being replaced, capable of grinding tough vegetation with an efficiency that no other dinosaur could match. As the flowering plants spread, with their different textures and nutritional profiles, the hadrosaurids would have adapted right alongside them. Some lineages might have become more specialized, focusing on particular types of plants in habitats. Others might have become more generalized, capable of thriving on whatever vegetation was available. The key point is that they wouldn't have stood still. Evolution never does. The ceratopsians, too, would have continued their radiation. In the late Cretaceous, they had already diversified into dozens of species across North America and Asia, varying in size from dog-sized to elephant-sized, sporting an astonishing variety of horn and frill configurations. Without the extinction, this diversity would have continued to expand. Perhaps some lineages would have become larger, filling niches that in our timeline would eventually be occupied by elephants and rhinoceroses. Perhaps others would have become smaller, more nimble, adapted to different habitats or different food sources. And the sauropods, those long-necked giants that had defined the Jurassic but seemed to be declining in diversity by the late Cretaceous, would have persisted as well. They were specialists, reaching food sources that no other herbivore could access. And as long as tall forests existed, they would have had a role to play. In our timeline, the extinction removed them before we could see how they might have adapted to a changing world. In our alternative timeline, they would have had the chance to prove their staying power. The world of 10 million years post-asteroid would have been recognizable to a visitor from the Cretaceous, but it would have been subtly different in 1,000 small ways. New species where old ones had been, new behaviors, new ecological relationships, new forms filling new niches. The dinosaurs weren't changing because the world forced them to change. The world was still warm, still forested, still fundamentally Mesozoic in character. They were changing because that's what life does. It explores possibilities. It fills available space. It diversifies. But the real changes were coming. Around 55 million years ago, the planet was about to experience something unprecedented. A sudden dramatic warming that would push global temperatures to levels not seen in tens of millions of years. The Paleocene-Eocene thermal maximum was approaching, and it would test the dinosaurs in ways they had never been tested before. The question was whether they were ready. Around 55 million years ago, something extraordinary happened to the Earth's climate. Within perhaps 20,000 years, a blink of an eye, in geological time, global temperatures spiked by 5 to 8 degrees Celsius. The polar regions, already warm by modern standards, became positively tropical. Palm trees grew in Alaska. Crocodilians basked on the shores of the Arctic Ocean. The deep oceans warmed by several degrees, fundamentally altering circulation patterns and marine ecosystems around the world. Scientists call this event the Paleocene-Eocene thermal maximum, or PETM, and it was one of the most dramatic climate shifts in the last 100 million years of Earth history. The cause was almost certainly a massive release of carbon into the atmosphere, perhaps from volcanic activity associated with the opening of the North Atlantic, perhaps from the destabilization of methane hydrates on the ocean floor, perhaps from some combination of both. The result was a greenhouse effect more intense than anything the dinosaurs had experienced since the Triassic. It was a test, and in our timeline, it reshaped mammalian evolution dramatically. Many species went extinct, others shrank in size because smaller bodies are easier to cool. New lineages appeared, adapted to the hothouse conditions. The primates that would eventually give rise to monkeys and apes first appear in the fossil record right around this time, as if the thermal crisis had opened new ecological doors even as it closed others. In our alternative timeline, the same crisis would have occurred. The PTM was driven by geological processes that had nothing to do with the asteroid impact, but it would have been dinosaurs, not mammals, facing the challenge. And here's the interesting thing. Dinosaurs might have been better equipped to handle extreme heat than mammals were. Think about the problem from a physiological perspective. Mammals are endotherms. They generate their own body heat internally and work hard to maintain a constant internal temperature, usually around 37 degrees Celsius. This is metabolically expensive and requires sophisticated cooling mechanisms, sweating, panting, seeking shade, restricting activity to cooler parts of the day. When ambient temperatures approach or exceed body temperature, these mechanisms become less effective. A mammal, in extreme heat, is working against thermodynamics, trying to dump heat into an environment that doesn't want to accept it. Large dinosaurs operated differently. They were probably gigantotherms. Their sheer mass meant that their body temperature remained relatively stable, regardless of external conditions, like a massive water tank that takes hours to warm up or cool down. They didn't need to generate as much metabolic heat as mammals because they could absorb heat from their environment during the day and retain it through the night. And because they didn't maintain the high, constant temperatures that mammals require, they weren't as vulnerable to overheating when the world got hot. The smaller dinosaurs had their own advantages. Many of them were feathered, and feathers are remarkably versatile insulators. They can be fluffed up to trap warm air in cold conditions, or sleek down and spread to allow heat dissipation in hot conditions. The same structure that would later help dinosaurs survive polar winters might have helped them survive equatorial summers during the PETM. The tropical regions during the Eocene hothouse might have become challenging even for dinosaurs, perhaps forcing migrations toward the poles, perhaps creating equatorial dead zones where temperatures simply exceeded what any large land animal could tolerate. But the poles themselves would have become paradise. Warm, wet, covered in lush forests, extending nearly to the Arctic and Antarctic circles. Perfect habitat for dinosaurs of all sizes, expanding into regions that had previously been marginal. But the land wasn't the only arena where evolution was playing out. In the oceans, our alternative timeline would have featured something that our actual history lacks entirely: the continued evolution of the great Mesozoic marine reptiles. In our timeline, the mosasaurs and plesiosaurs went extinct at the KPG boundary, victims of the same catastrophe that killed the land dinosaurs. The niches they left empty would eventually be filled by whales, which evolved from land-dwelling mammals over the course of the Eocene, one of evolution's great transformations. But in our alternative timeline, the marine reptiles never went extinct. They would have been there, already occupying those niches when the PTM reshaped the oceans. The mosasaurs of the late Cretaceous were at their peak, massive sea lizards, some reaching 15 meters in length, with powerful jaws and paddle-like limbs. They were the undisputed sovereign of the food chains of the shallow seas, filling roles similar to modern great white sharks and orcas. Without the extinction, they would have continued to evolve. Some lineages might have become more streamlined, faster, better adapted to hunting fish and squid in the open ocean. Others might have grown larger still, exploiting the abundant marine life of the Eocene hothouse. And the plesiosaurs, those strange, long-necked marine reptiles that had persisted for over 135 million years before the asteroid ended them, would have continued their own strange evolutionary journey. Their body plan, with 4 large flippers and a neck that could be longer than the entire body of many other animals, seems almost absurdly impractical to modern eyes. Yet it worked well enough to sustain them through the Jurassic and Cretaceous. Perhaps in the warming oceans of the Eocene, some plesiosaur lineages would have become more efficient hunters, their long necks evolving as ambush weapons, striking at schools of fish from unexpected angles. Perhaps others would have become filter feeders, straining plankton from the warming waters the way baleen whales do today. The point is that the oceans of our alternative timeline would have looked fundamentally different from the oceans of our actual history. Instead of whales and dolphins and seals, all descended from land mammals that returned to the sea, we would have seen the continued diversification of lineages that had been marine for hundreds of millions of years. The ecological niches would have been similar, but the animals filling them would have been unrecognizably different. On the coastlines, where land met sea, another group would have been thriving, the pterosaurs. In our timeline, they went extinct alongside the dinosaurs, leaving the skies to the birds. But in our alternative history, they would have persisted, and the warm, productive seas of the Eocene would have been ideal habitat for them. Picture a pterosaur the size of a small airplane, soaring over tropical waters, plucking fish from the surface, with a beak the length of a human arm. Picture colonies of smaller pterosaurs nesting on sea cliffs, filling the ecological roles that seabirds occupy in our world. Picture the skies of the Eocene shared between the pterosaurs and the birds. Both dinosaur lineages technically, but so different in form and history that they would have competed for some niches while dividing others. The Eocene hothouse lasted for millions of years, long enough for evolution to produce countless adaptations to its conditions. Somewhere around 50 million years ago, in our alternative timeline, the dinosaurs would have reached a kind of equilibrium with this warm world, diversified across every continent, dominant in nearly every terrestrial and aerial niche, sharing the oceans with their marine reptile cousins. It might have seemed to an observer at that moment that this was simply how the world worked, that dinosaurs were as permanent a feature of the Earth as the mountains and seas. But the climate doesn't stay constant forever. Even as the dinosaurs were flourishing in their hothouse Eden, the processes that would end it were already underway. India was crashing into Asia, raising the Himalayas, and the weathering of those new mountains would begin drawing carbon dioxide from the atmosphere. Antarctica was drifting toward the South Pole, and soon a new ocean current would isolate it from the warmth of the tropics. The long cooling was about to begin, and it would transform the Earth more profoundly than any asteroid ever could. The warmth couldn't last forever. Around 34 million years ago, the Earth began a long, slow slide toward colder conditions that would eventually culminate in the great glacial epochs of the Pleistocene. The immediate trigger was Antarctica. For millions of years, the southern continent had been connected to South America by a narrow land bridge, and warm ocean currents from the tropics had been able to reach its shores, keeping it relatively mild, despite its polar position. But as the continents drifted apart, a new ocean current formed, the Antarctic Circumpolar Current, that isolated Antarctica from the warmth of the rest of the world. Ice sheets began to form on the continent for the first time in hundreds of millions of years. The planetary thermostat had been turned down, and it would never fully recover. The effects rippled outward from the poles. Global temperatures dropped by several degrees. Sea levels fell as water became locked up in Antarctic ice. Rainfall patterns shifted as the temperature gradients between equator and poles steepened, and the forests, those endless pole-to-pole forests that had characterized the age of dinosaurs, began to retreat. This was something new. For 150 million years, since before the first dinosaur walked the Earth, the planet had been a greenhouse world, warm and wet, covered in vegetation from the Arctic to the Antarctic. Dinosaurs had evolved in this world, diversified in this world, conquered every continent in this world. They had never faced a planet where ice sheets covered significant portions of the land, where winters could be genuinely harsh, where forests gave way to something else entirely. The Oligocene cooling was a test unlike any they had experienced before. But here's where we need to challenge a common assumption. We tend to think of dinosaurs as tropical animals, creatures of warm climates that couldn't possibly survive in cold conditions. After all, they're often depicted in steaming jungles, their massive bodies soaking up the warmth of a prehistoric sun. And the comparison to modern reptiles seems to reinforce this impression. Snakes and lizards don't do well in cold climates, which is why you don't find them in Antarctica. The problem with this assumption is that it's almost certainly wrong. We now know that dinosaurs lived in polar regions during the Mesozoic, Fossil sites in Alaska and Antarctica have yielded dinosaur bones from latitudes that would have experienced months of winter darkness, temperatures that regularly dropped below freezing. These weren't occasional visitors or lost wanderers. They were established populations, breeding and raising their young in conditions that we would consider harsh by any standard. The famous Prince Creek Formation in northern Alaska preserves a diverse dinosaur ecosystem from about 70 million years ago, including hadrosaurs, ceratopsians, and tyrannosaurs, all living year-round above the Arctic Circle. How did they do it? The answer was literally covering their bodies. Feathers. For many years, we have known that a surprisingly wide variety of dinosaurs, not just the tiny bird-like theropods, had feathers. Feathers have been found on tyrannosaurs, on ornithischians, on dinosaurs large and small, from lineages across the family tree. Feathers were originally used for insulation rather than flight. In situations where a naked reptile would have gone into torpor, they evolved to keep dinosaurs warm by trapping body heat against the skin. In our alternative timeline, this adaptation would have proved crucial as the world cooled. As the ice moved forward, the feathered theropods, already endowed with nature's most adaptable insulation, would have been able to spread into colder environments. Picture a pack of medium-sized theropods, their bodies covered in thick plumage that ruffles in the frigid wind, hunting across a snowy landscape that would have been unthinkable in the Mesozoic. These creatures would have looked remarkably bird-like because they were essentially birds that had never given up hunting on the ground. For the larger dinosaurs, the situation was different. A 15-meter sauropod couldn't rely on feathers for insulation the way a 2-meter theropod could. The surface area to volume ratio doesn't work in their favor. However, gigantothermy is reciprocal. The same thermal inertia that helped large dinosaurs survive the Eocene heat would have helped them survive moderate cold. Short cold snaps wouldn't have had much of an impact on them because their massive bodies would have changed temperature so slowly. They might have migrated seasonally, following the warmth and the food, the way many large mammals do today. Alternatively, they may have merely been confined to equatorial areas, leaving the higher latitudes for their more diminutive and adaptive relatives. An intriguing question is raised by the ornithischians, ceratopsians, hadrosaurs, and ankylosaurs. Although some specimens indicate they had filamentous integuments that may have had a similar function, we lack concrete proof that they were feathered. According to our alternate timeline, these lineages may have evolved thicker, more insulating body coverings due to the selective pressure of cooling climates. Imagine an Oligocene ceratopsian with a thick layer of protofeathers covering its body. Its enormous frill may have been scaled back from the ornate displays of its Cretaceous forebears to something more functional and streamlined to withstand the cold. It would have looked something like a woolly rhinoceros, but with the unmistakable silhouette of a horned dinosaur. But the most profound change wasn't in the dinosaurs themselves. It was in the world they inhabited. As the climate cooled and dried, the endless forests began to break up. Because trees need specific minimum temperatures and amounts of rainfall to flourish, the forests withdrew as these conditions moved closer to the equator. Something new was emerging in their place. Open landscapes, woodlands with gaps between the trees, meadows and clearings where sunlight reached the ground. These weren't yet the great grasslands that would later transform the planet, but they were the beginning of something. The era of open spaces was starting to emerge, and the era of forests was coming to an end. For dinosaurs that had spent 150 million years in forests, this was a profound environmental shift. The survival rules were shifting. You can hide in a forest, ambush prey, or stay out of sight of predators. Size matters less than stealth, and speed matters less than maneuverability. However, there is nowhere to hide in an open area. You survive by being fast enough to escape, or big enough to fight, or vigilant enough to spot danger before it's too late. Since many eyes are better than two, herding becomes advantageous. Long-distance running becomes more valuable than short sprints. These are exactly the pressures that would reshape mammal evolution in our timeline. producing the horses and antelope, the wolves and big cats that came to dominate open ecosystems. Dinosaurs would have been subject to the same pressures in our alternate timeline. It's possible that the outcomes would have been remarkably similar, not because dinosaurs would have developed into mammals, but rather because similar ecological issues typically lead to similar solutions. A fast-running herbivore is a fast-running herbivore, whether it's a horse or an ornithomimid, whether it is a wolf or a derived theropod. A pack-hunting predator is a pack-hunting predator. The Oligocene was a transition, a bridge between the warm forests of the Eocene and the grasslands that were coming. Compared to their Cretaceous ancestors, the dinosaurs that arose from it would have been more suited to cold climates and open environments, and they would have started to acquire the specializations required by the new environment. They had survived their first major test. But the real transformation was still to come. Around 23 million years ago, a humble family of plants would begin a conquest that would reshape every continent except Antarctica. Grass was about to change everything. Grass doesn't seem like a revolutionary organism. It's humble, low to the ground, easily overlooked. You walk on it, mow it, forget it exists. But starting around 23 million years ago, in the early Miocene, grass began a conquest that would transform the face of the Earth more thoroughly than any asteroid impact. By the time it was finished, grass would make up about 40% of the planet's land area and establish completely new ecosystems that didn't exist during the first 400 million years of land life. To understand why grass was so revolutionary, you need to understand what makes it different from other plants. Most plants grow from their tips, damage the top of a tree, and you've removed its growing point, stunted its development, perhaps killed it entirely. But grass grows from its base. It just grows back from below if you cut it, burn it, or scrape it down to stubble. Because of this, it is nearly impossible to kill grass by fire or browsing. It's the plant equivalent of a hydra. Remove its head, and it grows right back. Grass also produces silica phytoliths, microscopic particles of glass embedded in its tissues. Because of these, grass becomes tough, abrasive, and challenging to digest. Any animal that tries to eat grass is essentially chewing on sandpaper, wearing down its teeth with every bite. The evolution of hypsodont teeth, the high-crowned, constantly growing teeth found in horses, cattle, and other grazing mammals, was fueled by this in our timeline. Animals that couldn't evolve solutions to the grass problem simply couldn't exploit the new grassland ecosystems. One of the planet's greatest ecological opportunities was closed off to them. The spread of grasslands was driven by the same cooling and drying that had begun in the Oligocene. Forests withdrew to wetter regions close to rivers and coasts as rainfall declined throughout the continental interior. Grass grew in the open areas between them because it could withstand the conditions when trees could not because it preferred them. As they occupy the marginal areas that nothing else can, grasslands can be thought of as the vegetative equivalent of hardy survivors. According to our timeline, one of the major adaptive radiations in the history of mammals was initiated by the Miocene grasslands. Horses evolved from small forest dwellers into the large, fast-running grazers we know today, because of their sophisticated, multi-chambered stomachs, which enable them to extract nutrition from tough plant material that other mammals are unable to digest. Ruminants, cattle, deer, and antelope have undergone explosive diversification. Predators evolved to match. The ancestors of wolves and big cats became faster, more social, better adapted to hunting in open terrain. The modern African savanna, with its herds of wildebeest and zebra, its prides of lions and packs of wild dogs, is the culmination of 20 million years of evolution in grassland ecosystems. In our alternative timeline, the grasslands would have spread just as they did in our history. The animals that were present had nothing to do with the climate patterns that produced them. The distinction is that dinosaurs, rather than mammals, would have had to adjust to this new environment, and the pressures would have been identical. Run quickly or perish. eat grass or starve, or become prey when predators approach. The results would have probably been strikingly similar due to the unyielding logic of natural selection. Consider the ceratopsians, the horned dinosaurs that had dominated the herbivore niches of late Cretaceous North America. They had been browsers in the forests, harvesting vegetation with their parrot-like beaks and processing it with their shearing teeth. However, those teeth weren't made for grass. They would have worn down quickly against the silica-laden tissues, leaving the animals unable to feed efficiently. The ceratopsians that survived in a grass-dominated world would have been those that evolved solutions to this problem. One theory is the development of constantly expanding teeth, like those found in horses and rodents. Dinosaurs have the developmental pathways necessary for ongoing tooth growth. We see hints of it in the dental batteries of hadrosaurs, where teeth were constantly being replaced from below. If a ceratopsian lineage had developed truly hypsodont teeth, it could have continued to graze indefinitely, simply growing new teeth to replace the ones that were worn down by the grass. Imagine a Triceratops descendant that evolved from its Cretaceous ancestor 20 million years ago. You can still identify it as a ceratopsian. The proportions have changed, but the basic body plan is too good to give up. The head is lower to the ground, longer, and more suited for grazing than browsing. It is shaped like a living lawnmower and has a wider, more squared-off beak that is intended to harvest grass in large areas. The frill has shrunk, no longer needed for display or thermoregulation in the same way. Instead, the enormous jaw muscles required to break down tough vegetation received the energy. Like wildebeest in the Serengeti, it travels across the Miocene prairies in herds of hundreds, a river of horn and flesh. But grazing brings its own dangers. In a forest, you can hide from predators. On an open plain, you're visible from kilometers away. The only defenses are vigilance, numbers, and speed. The herding behavior of Miocene ceratopsians wouldn't have been optional. It would have been necessary to survive. On an open plain, a lone grazer is a dead grazer. With hundreds of eyes watching the horizon, a 1,000-strong herd has a chance. The ornithomimosaurs, the ostrich dinosaurs of the Cretaceous, were already pre-adapted for grassland life in some ways. They had light bodies, long legs, and were quick runners. Given their ability to utilize a range of food sources, they were most likely omnivores. In a world of open plains, they might have become the ecological equivalents of antelope and gazelles, quick, vigilant, herd-oriented, and dependent on speed to elude predators. Imagine an ornithomimid from the Miocene, with legs even longer than those of its ancestors, and a body designed to run on flat ground for extended periods of time. Because of its long neck, it can see over the grass and detect danger coming from any angle. It feeds on a mixture of grass seeds, insects, and small animals, an opportunistic diet that allows it to thrive in environments too harsh for specialists. It can outrun any predator that depends solely on pursuit when it is in danger, reaching speeds of up to 60 kilometers per hour. It lives in groups of dozens, and when one individual spots danger and bolts, the others follow instantly, a wave of panic spreading through the herd faster than any predator can react. An intriguing example is the hadrosaurs. The rows of hundreds of interlocking teeth in their complex dental batteries were already the most effective plant processing devices that a dinosaur had ever developed. They were able to handle tough vegetation that would have defeated other herbivores because they were, in a sense, pre-adapted for grazing. Perhaps, in our alternative timeline, the hadrosaurs would have become the dominant grazers, their existing adaptations giving them a head start in the competition for grass. However, considering the principles of evolutionary competition, another possibility appears more plausible. Perhaps no single lineage would have dominated. In the same way that the African savanna is currently shared by wildebeest, zebra, buffalo, gazelle, and a dozen other species, each of which uses the grassland in a unique way, it is possible that the Miocene grasslands would have been divided among several dinosaur groups, each of which specialized in slightly different niches. The ecological theatre had been rebuilt. The forest stage that had hosted the Mesozoic drama was being struck, replaced by an endless plain of waving grass under an open sky. Any actors who were willing to learn new lines could take on new roles. The dinosaurs had mastered forest life over a period of 150 million years. They now had about 20 million years to learn something completely different. The question was, what would be hunting them? Because predators would need to adapt as well in a world where herds move quickly. The Tyrannosaurus rex was the late Cretaceous's top predator, a car-crushing bite force, 6 tons of lethal power, and 12 meters of muscle and bone. Its sole purpose was to use overwhelming force to defeat large prey. This tactic was extremely effective in Mesozoic forests, where ambush was feasible and prey could not see you approaching until it was too late. T. rex sat at the top of its food chain for millions of years, unchallenged, seemingly perfect. But perfection is always relative to environment. Change the environment and perfection becomes obsolescence. The open grasslands of the Miocene would have been hostile territory for a classic tyrannosaur. A 6-ton predator in a forest can conceal itself behind trees and get close enough to strike its prey before they even realize it's there. On an open plain, there's no hiding a predator that stands 4 meters tall at the hip. Prey animals can see you coming from kilometers away. They're running by the time you're close enough to launch an attack, and you, with your massive body and relatively short legs, cannot catch them. The tyrannosaur lineage would not have become extinct as a result. Successful body plans are not easily abandoned by evolution, but it does mean they would have had to change. And since we've seen it happen before with mammalian predators under similar pressures, we can predict the direction of that change. The tyrannosaurs of the Miocene grasslands would have become leaner. Faster, lighter, more efficient runners would have been preferred by natural selection. T-Rex's stocky body plan would have thinned and stretched over millions of years, with longer legs in relation to body mass, a more horizontal posture for improved balance at speed, and possibly a smaller head to lessen the weight on the front of the body. The end product might have resembled a scaled-up version of the earlier tyrannosaurs, such as Guanlong or Dailong, which were considerably lighter in build than their later offspring. However, even a smaller tyrannosaur would have encountered a basic issue. The largest prey animals would have been herd animals, and hunting herd animals alone is dangerous and inefficient. A lone wolf can't bring down a healthy bison. A mature buffalo cannot be taken by a lone lion. The prey is too large, too dangerous, too surrounded by companions that might fight back. The solution, discovered independently by wolves and lions and African wild dogs, is cooperative hunting, working together in groups to isolate, exhaust, and overwhelm prey that no single individual could take. Here's where we encounter an interesting question about dinosaur behavior. Whether or not large theropods hunted in packs is unknown. There's some evidence, trackways that seem to show multiple individuals moving together, bone beds that contain many predators alongside their apparent prey, but it's ambiguous. Tyrannosaurs may have been social hunters, according to some paleontologists. Others think they were solitary, perhaps only coming together to scavenge or breed. We must use ecological principles to make decisions when there is uncertainty. Furthermore, it is highly likely that grassland tyrannosaurs would have evolved into pack hunters based on ecological principles. They would have been hunting big, dangerous, herd-dwelling dinosaurs, which would have been nearly impossible to capture in any other way. This isn't because grasslands are magical. The selective pressure would have been intense. Individuals that could cooperate would have eaten. Individuals that couldn't would have starved. That's enough pressure over millions of years to change behavior, develop coordinated and communicative brains, and establish previously unheard of social structures. Imagine a group of 6 or 8 Miocene tyrannosaurs traversing the grassland in the early morning light. Although they are smaller than their Cretaceous predecessors, perhaps 7 meters long as opposed to 12 and 3 tons as opposed to 6, they are quicker, more nimble, and collaborate more effectively than T. Rex never needed. They're spreading out after spotting a herd of grazing ceratopsians in the distance. Some are circling widely to block escape routes, while others are going closer to push the herd in the direction of the ambush. When they attack, it's not the overwhelming assault of a single giant predator, but a coordinated strike from multiple angles, each individual knowing its role, working together to bring down prey that none of them could kill alone. However, there were other theropod lineages that adapted to the grasslands besides the tyrannosaurs. Alongside them, the smaller predators, the dromaeosaurids, troodontids, and other maniraptoran theropods would have been developing to occupy various ecological niches. Compared to the tyrannosaurs, these smaller predators were somewhat more pre-adapted to hunting in grasslands. They were already fast runners. Many of them already seem to have been social, hunting in groups based on the fossil evidence we have. They had prehensile digits that could manipulate objects, forward-facing eyes that provided excellent depth perception, and relatively large brains for their body size. The grasslands would have rewarded all of these traits. The dromaeosaurids, the raptor dinosaurs popularized by Jurassic Park, would have been particularly well suited to pack hunting on the open plains. Because of their rapidity and agility, they were already pursuit predators. Their well-known sickle claws were most likely used to hold prey in place, while the jaws delivered lethal bites, a tactic that is more effective when several people can attack at once. In our alternate history, the dromaeosaurid lineages may have evolved to play roles akin to those of contemporary wolves and wild dogs, pack hunters who pursue prey by tenacity rather than ambush. Imagine a group of 2-meter-long Miocene dromaeosaurids with streaked feathers that contrast with the grass. They hunt in groups of 20 or more, communicating through calls and body language, coordinating their movements across kilometers of open terrain. Their approach is straightforward but successful. Choose a target, pursue it until it exhausts itself, and alternately apply pressure while others take a break. African wild dogs still employ this tactic, and it works incredibly well against prey that depends on speed to survive. No animal can run at maximum speed forever. Eventually, fatigue prevails. The troodontids represent perhaps the most intriguing possibility. These tiny, light-built theropods had the largest brain-to-body ratio of any known dinosaur, making them the intellectuals of the dinosaur world. We'll explore their potential in more detail in the next chapter, but they would have been formidable grassland predators in their own right, probably hunting smaller prey that the larger predators ignored, perhaps developing more sophisticated social structures than any of their relatives. In our alternate timeline, predators of all sizes would have patrolled the Miocene grasslands, making them a killing ground. At the top, packs of slimmed-down tyrannosaurs, still the largest land predators on Earth, but fundamentally transformed by 50 million years of adaptation to new conditions. Packs of dromaeosaurids were in the middle, using their sheer endurance to run down prey. Troodontids and other small theropods are at the bottom, hunting everything from insects to rodent-sized mammals. The lone giant's era was coming to an end. The solitary tyrannosaur, killing through overwhelming individual power, was giving way to something new. Predators that succeeded through cooperation, coordination, perhaps even the beginnings of something we might call strategy. Brains were becoming just as vital as brawn in a world of wide plains and watchful herds. And that raises a question that paleontologists have debated for decades. Could dinosaurs have developed true intelligence if they had had enough time, say, an additional 50 million years? Could their minds have grown to the point where they could comprehend the world, make plans for the future, and ask questions about their own existence? You might be surprised by how difficult the solution is. In 1982, a Canadian paleontologist named Dale Russell published a thought experiment that would become one of the most famous and most controversial pieces of speculative paleontology ever written. Russell had been researching the late Cretaceous troodon, a small theropod dinosaur distinguished by an abnormally large brain in relation to its body size. Russell posed a straightforward query. in light of this lineage's tendency toward larger brains. What if the dinosaurs hadn't gone extinct? After an additional 66 million years of evolution, what might Troodon's descendants have evolved into? The dinosauroid, a hypothetical creature with 2 legs, manipulative hands with opposable digits, and a large rounded brain case that could contain human-level intelligence, was his response. Russell even commissioned a sculpture of his dinosauroid, and the result was strikingly humanoid. 2 forward-facing eyes, a vertical posture, a body plan that looked more like a grey alien than a dinosaur. It was obvious what was implied. Given enough time, dinosaurs might have evolved intelligence comparable to our own. There may have been competition between us. The public was captivated by the dinosauroid theory, but other scientists criticized it almost immediately, and in the decades that followed, the criticism has only grown. The problem isn't the idea that dinosaurs might have become more intelligent. We have evidence to support that reasonable speculation. The problem is the assumption that intelligence inevitably leads to a humanoid body plan. Russell's reasoning went something like this. Intelligence requires a large brain. A large brain requires an upright posture to balance it on the spine. An upright posture requires the forelimbs to be free from locomotion. Free forelimbs naturally evolve into manipulative hands. Any intelligent creature will therefore eventually resemble a human in appearance. It's a seductive argument, but it's almost certainly wrong. Consider the most intelligent, non-human animals alive today. Parrots and crows have shown cognitive capacities comparable to those of great apes. They use tools, solve complex problems, recognize themselves in mirrors, and appear to understand concepts like cause and effect. Yet they look nothing like humans. They're birds, with wings and beaks, and bodies shaped by 150 million years of avian evolution. Their intelligence evolved within the constraints of a very non-humanoid body plan, and those constraints didn't prevent them from becoming remarkably smart. For example, octopuses can use tools, solve puzzles, and seem to have somewhat distinct personalities. An octopus is about as far from a humanoid body plan as you can get. 8 arms, no skeleton, a distributed nervous system with neurons in each tentacle. Yet they're among the most intelligent invertebrates on Earth, perhaps among the most intelligent animals, period. The lesson is that evolution is not aiming for intelligence. Similar to venom, wings, or claws, it is a tool that develops when selective pressures favor it. And it can evolve in bodies of almost any shape, because intelligence is ultimately about information processing, not about having hands or standing upright. So what would intelligent dinosaurs actually have looked like? Probably like dinosaurs. After an additional 66 million years of evolution, the troodontids of our alternate timeline would still be identifiable as theropod dinosaurs. They would have retained the basic body plan that had served their ancestors so well. Bipedal movement, a horizontal stance supported by a long tail, forelimb grips, and a sharply tipped head. What would have changed was inside that head. The troodontid brain was already large for a dinosaur. The encephalization quotient, a measure of brain size relative to body size, was higher in Troodon than in any other known dinosaur. The troodontid brain may have continued to grow if the selection pressures we covered in the previous chapter continued to favor cognitive ability, if pack hunting required improved coordination, if grassland life required improved spatial memory, or if complex social structures required identifying individuals and remembering relationships. How far? There is no way to know for sure. However, we can find hints by examining the fate of birds, the only dinosaur lineage to survive the extinction. The brain-to-body ratios of crows and parrots are similar to those of great apes, and they reached that degree of encephalization in about the same 66 million years as our hypothetical troodontids. It's not unreasonable to suppose that a lineage starting with Troodon's already impressive brain might have reached similar levels. Picture a troodontid of the late Miocene, perhaps 10 million years ago, in our alternative timeline. Its feathers, which range in color from gray on the back to white on the belly, help it blend in with the open grasslands. where it hunts. It is roughly 2 meters long from snout to tail tip. Its large, forward-facing eyes offer superior binocular vision. Its brain, contained in a skull that protrudes noticeably at the back, is the largest of any land animal on Earth in proportion to its body size. Its hands, which still have 3 clawed fingers, are able to grasp and manipulate objects with a precision that its Cretaceous ancestors could not have achieved. This creature is intelligent, not human intelligent, as we will see in a moment, but intelligent in ways that are crucial to its survival. It hunts in packs of 10 to 20, and the coordination of those hunts is amazing. They use flanking maneuvers, diversionary tactics, and even what seems to be intentional deception, with some individuals pretending to be injured in order to entice prey into ambushes. It uses simple tools: sticks to probe burrows for hidden prey, rocks to crack open hard-shelled food items. It has a complex vocal repertoire, dozens of distinct calls that communicate information about predators, food sources, and social status. Instead of depending only on instinct, young troodontids observe and mimic the behaviors of their elders. In many respects, this animal would have filled an ecological niche akin to that of early hominids or contemporary wolves. A social predator whose success depends more on teamwork than on physical prowess. It would have been formidable, adaptable, capable of thriving in environments across the globe. But it would not have built cities. It would not have advanced philosophy, mathematics, or writing. It would not have asked questions about the stars, or wondered about its place in the universe. Why not? Since human-level intelligence is based on a very specific set of circumstances that, as far as we can tell, happened exactly once in the history of life on Earth, it is not about having a large brain. Primates, a lineage that had already spent tens of millions of years creating intricate social structures, manipulative hands that could grasp branches, and brains that could navigate three-dimensional environments, are where human intelligence originated. After being driven from the trees, our ancestors encountered fresh, selective pressures on the African savanna, finding food in a difficult setting, working in teams, and conveying complicated information about hazards and resources are all necessary. Our brains expanded dramatically over just a few million years, driven by a feedback loop between social complexity and cognitive ability. Numerous factors, each necessary but insufficient on its own, were necessary for this series of events to occur. Although primates made it to Africa, none of the 3 lineages that made it to North America developed large brains. Although grasslands were found on all continents, only in Africa did they give rise to a species that was able to think abstractly. Intelligence of some kind might be common in the universe, but intelligence like ours, capable of technology and science and philosophy, might be vanishingly rare. Perhaps as intelligent as chimpanzees, dolphins, or crows, our substitute troodontids would have been. They might have used tools, formed complex societies, passed knowledge from generation to generation. No matter how many millions of years it took to evolve, the spark that transformed our ancestors from intelligent apes to curious humans might never have happened in a dinosaur lineage. Thoughtful creatures could have been produced by the dinosaurs, but not ones that questioned the nature of their thought processes. And yet, there's something almost comforting in that limitation, because it means that in our alternative timeline, the Earth would have remained wild, beautiful, and brutal, and utterly indifferent to meaning. A planet full of animals acting like animals, with no one to judge it as great or awful, or wonder if it had any purpose at all. The dinosaurs would have ruled for 230 million years, unchallenged, unmarked by any species capable of recording their existence. Because no one would be aware that we might have been there, nobody would miss us in that world. 2.5 million years ago, the Earth crossed a threshold. The long cooling that had begun in the Oligocene, that had transformed tropical forests into temperate woodlands and woodlands into grasslands, finally reached its logical, the final cosmic convergence. Ice sheets began to form in the northern hemisphere, not just on isolated mountain peaks, but spreading across entire continents, burying Scandinavia and Canada under kilometers of frozen water. A climate regime unlike anything the planet had seen in more than 250 million years, had emerged with the start of the Pleistocene. The ice did not move forward or remain. Rather, it pulsed, moving forward during roughly 100,000-year-long glacial periods, and backward during 10,000, 20,000-year-long interglacials. More than 20 of these cycles occurred during the Pleistocene, each of which altered the planet's topography, pushed ecosystems closer to the equator, and then allowed them to recover, formed and destroyed land bridges, and forced species to either adapt or perish. In our timeline, this era produced the iconic megafauna of the Great Glacial Epoch: woolly mammoths with their shaggy coats and curved tusks, woolly rhinoceroses built like furry tanks, cave bears that stood 3 meters tall on their hind legs, giant ground sloths the size of elephants. These animals' large bodies to retain heat, thick coats of fur or fat for insulation, and capacity to endure the long winters on little vegetation are all products of their unique evolutionary adaptation to glacial conditions. They were the animals that defined their era. In our alternative timeline, there would have been no mammoths, no woolly rhinos, no giant sloths. Something completely different would have filled those niches: large, cold-adapted herbivores. They would have been filled by dinosaurs. Whether dinosaurs could have survived the Great Glacial Epochs at all is the question. They have never faced a challenge that would force them to step outside of their evolutionary comfort zone as much as this one. For 200 million years, dinosaurs had thrived in a greenhouse world, warm, wet, forested. Although the Miocene grasslands had undergone a substantial transformation, Pleistocene temperatures had remained moderate. They would now have to endure winters with temperatures as low as -40 degrees Celsius, 8 months of snowfall, a severe shortage of food, and the need to migrate or endure months of starvation in order to survive. Could they do it? We have grounds to believe that they might. During the Cretaceous, dinosaurs lived year-round above the Arctic Circle in Alaska's Prince Creek Formation. Keep in mind that many dinosaur lineages were already outfitted with nature's best cold-weather gear, and that feathers evolved specifically for insulation. Remember that birds, living dinosaurs, thrive in some of the coldest environments on Earth today, from penguins in Antarctica to snowy owls in the Arctic tundra. The necessary adaptations for Pleistocene survival would have been substantial, but they wouldn't have necessitated a fundamental transformation of dinosaurs. They would have needed them to become more of their current selves. Think about the horned herbivores, known as ceratopsians, which had already adapted to life in grasslands during the Miocene. A Pleistocene ceratopsian would have been a magnificent creature. Imagine a triceratops that has undergone 60 million years of adaptation to harsher environments. Its body would have been massive, perhaps 8 or 9 meters long, bulked up with fat reserves that could sustain it through the lean winter months. Its frill, which was formerly mainly used for thermoregulation and display, would have thickened and shrunk, becoming less decorative and more practical, and covering its entire body, from the tip of its nose to the end of its tail, would have been a dense coat of feathery integument, the thick, insulating down of an animal designed to survive in extremely cold temperatures, not the ornate feathers of a tropical bird. Imagine this animal traveling through a grassy and low shrubby landscape in a herd of hundreds on the Siberian steppe during an interglacial period. At first glance, it appears nearly mammalian. That huge bulk, that shaggy coat. However, the silhouette clearly resembles a dinosaur. The four-legged stance, the beaked face, the horns protruding from the brow. Its dental battery grinds plant material more efficiently than any mammal, allowing it to consume hardy, low-growing vegetation. When winter comes, it will migrate south, following the retreating warmth, returning north only when the snows melt and new growth appears. The hadrosaurs would have encountered comparable challenges and probably came up with comparable solutions. They would have thrived on a diet of hardy Arctic vegetation thanks to their sophisticated feeding apparatus, those dental batteries with hundreds of interlocking teeth. Animals with low, wide, and highly insulated bodies that walked on all fours most of the time had long since replaced their bipedal ancestors. In the winter months, they would have congregated in valleys that offered some protection from the wind, huddling together for warmth, the way musk oxen do today. The predators would have also adjusted. Descended from the pack-hunting lineages of the Miocene, a Pleistocene tyrannosaur would have been a nightmare creature. It would have been smaller than its Cretaceous ancestors, possibly only 5 meters long, but it would have been almost undetectable against a snowy background, thanks to its thick coat of white and grey feathers. It would have hunted in organized packs, using cooperation and perseverance to take down prey many times its own size. In the depths of winter, when prey was scarce, it might have been able to slow its metabolism and enter a torpor-like state, surviving on stored fat until spring brought new opportunities. But not all dinosaurs would have adapted to the cold. In order to survive in equatorial refugia, where temperatures remained moderate, even during the glacial maxima, some lineages would have withdrawn to the tropics. South America, isolated by the Central American Seaway for much of the Cenozoic, might have become a repository of ancient forms. Descendants of Cretaceous lineages that had never needed to adapt to cold or grasslands, preserved in tropical forests like living fossils. In an increasingly cold world, Southeast Asia and Central Africa would have played similar roles as islands of warmth. As a result, the planet would have been more sharply divided into climatic zones than it has ever been since the emergence of the dinosaurs. Something akin to the ancient Mesozoic world might have survived in the tropics, warm, wooded, and home to dinosaurs that a visitor from the Cretaceous would have recognized. Something new would have appeared in the polar and temperate regions. Dinosaurs transformed by 60 million years of adaptation to conditions their ancestors never imagined, as different from Tyrannosaurus and Triceratops as mammoths were from their tropical elephant ancestors. The dinosaurs would have been put to the test more severely during the Great Glacial Epochs than during any other period in their 200 million year history. Some lineages would have failed the test, going extinct as the climate pushed them beyond their limits. Others would have survived it, hardened and adapted from the glacial cycles, prepared for whatever lay ahead. And we were the next thing on our timeline, a species of clever ape that walked out of Africa and spread across the globe, hunting megafauna to extinction, reshaping ecosystems, eventually building civilizations that could ponder the deep history of their planet. That species would not have existed in our alternate timeline. The conditions that produced human intelligence, the specific sequence of events in African primate evolution, would have played out differently. Or not at all. Without anyone to identify it, the Pleistocene would have come to an end. However, the glacial cycles themselves would have persisted, moving forward and backward according to their 100,000-year cycle. The dinosaurs of the frozen world would have migrated, adapted, and survived with each cycle, just as they had with everything else the planet had thrown at them. After 230 million years, they had become the ultimate survivors. Another obstacle was the ice. They had also encountered it. There's a rule in biology called Bergmann's rule, and it's remarkably simple. Within a species or lineage, individuals tend to be larger in colder climates. Thermodynamics is the cause. A larger body loses heat more slowly because its surface area to volume ratio is smaller. In a cold environment, being big is an advantage. Your body can hold on to heat more effectively. To get through difficult times, you can store more fat. You can just put up with things that would kill a lesser animal. Bergmann's rule shaped the megafauna of our Pleistocene. Compared to their relatives, tropical elephants, woolly mammoths were larger. Cave bears dwarfed modern brown bears. The 3.5-meter-long antlers of the giant deer of Ireland were ridiculously large, almost comically oversized, but they were supported by a massive body. Giants were created by cold. The same rule would have held true in our alternate timeline, and it would have resulted in giants of a completely different type. The ceratopsians of the Pleistocene steppes would have been the largest members of their lineage since the days of the Cretaceous. Perhaps larger, a full-grown adult might have measured 10 meters from beak to tail, standing 2.5 meters at the shoulder, weighing 8 or 9 tons. Its horns would have been shorter than those of Triceratops, less elaborate, more functional, weapons for defense against predators and competition for mates, rather than the ornate display structures of its ancestors. Its body would have been barrel-shaped, filled with the fermentation chambers and fat reserves required to process massive amounts of low-quality vegetation during the short Arctic summer and survive the long winter on stored energy. These animals would have moved in herds that darkened the horizon, not dozens or hundreds, but thousands. Rivers of flesh flowing across the mammoth steppe, following the seasonal pulse of vegetation growth. During the summer, they would have moved northward into the high Arctic to graze on the abundance of plants created by the unending daylight. They would have moved southward during the winter, gathering in valleys with shallower snow and some vegetation still reachable. The scale of these migrations would have been staggering. Millions of animals moving in synchrony across thousands of kilometers. One of the great wildlife spectacles of the planet. The hadrosaurs would have shared these grasslands, their populations perhaps even larger than the ceratopsians. Their ability to walk on 2 or 4 legs may have been helpful in deep snow, where they could rear up to browse on shrubs and low trees when ground-level vegetation was buried, and their dental batteries gave them an advantage in processing the toughest vegetation. Imagine a 7-meter-long Pleistocene hadrosaur with a duck-like bill designed for cropping vegetation near frozen ground and a thick coat of filamentous feathers covering its body that trapped warm air against its ponts. Skin, it travels through a snowstorm in a herd of several hundred animals, their breath creating clouds in the freezing air as they crouch close to one another for warmth. But the northern steppes were only part of the story. Each of the diverse habitats that made up the Pleistocene world would have produced its own distinctive dinosaur fauna. Beringia, the land bridge that connected Asia and North America during glacial periods, would have been a highway for dinosaur migration, just as it was for mammoths and humans in our timeline. Species that evolved in Asia would have crossed to the Americas and vice versa, creating a shared fauna across the northern continents. With only a few thousand kilometers of continuous habitat separating them, the tyrannosaurs of Siberia and Alaska would have been cousins. The ceratopsians of Wyoming and Mongolia would have interacted. It would have been a single great ecosystem, stretching from France to Florida, united by the cold. Something quite different would have been preserved in the tropical refugia further south. In the Amazon basin, in the Congo, in Southeast Asia, fragments of the old forest world would have persisted through the glacial cycles, warmed by their equatorial location, even as ice sheets buried the higher latitudes. Here, you may have discovered dinosaurs that resembled those of the Cretaceous, small theropods hunting in the understory, and sauropods still browsing in the canopy, a world that time had all but forgotten. When the ice receded, these refugia would have been islands of biodiversity, protecting lineages that had become extinct elsewhere and acting as sources for recolonization. The frozen world's predators would have been just as magnificent as their victims. In the Pleistocene, the pack-hunting tyrannosaurs we envisioned in previous chapters would have peaked, their hunting techniques perfected, and their social structures refined by millions of years of evolution. A pack of Pleistocene tyrannosaurs taking down a full-grown ceratopsian would have been a spectacle of coordinated violence, some individuals driving the prey, others cutting off escape routes, still others waiting in ambush, the whole group working together with a precision that spoke to generations of learned behavior, passed from parents to offspring. Smaller predators would have filled other niches. The dromaeosaurids, those feathered pursuit hunters, would have been common on the open steppes, hunting in packs that could number in the dozens, taking down mid-sized prey through sheer persistence. The troodontids, those large-brained, tool-using hunters we imagined in Chapter 9, may have evolved into the most adaptable predators of all, able to capture a variety of prey through a combination of intelligence, cooperation, and adaptability. Solitary hunters may have stalked the forest edges, ambushing prey from cover. The Pleistocene fauna of the seas would have been unique, The same frigid waters that supported whales and seals in our timeline would have been traversed by the mosasaur and plesiosaur lineages, which by now had diversified into dozens of species, occupying niches ranging from coastal fish-eaters to open ocean giants. Some may have converged on the body plans of marine mammals by developing thick layers of blubber for insulation. Others might have become seasonal migrants, following prey species between tropical and waters. The largest descendants of the great marine reptiles of the Mesozoic might have rivaled the great whales in size, filter feeding on krill and small fish in the productive polar seas. A rhythm of expansion and contraction, extinction and speciation, and adaptation and readaptation would have been produced by the glacial cycles. With each ice advance, species would have been forced closer to the equator, resulting in population fragmentation and chances for divergence. Each retreat would have allowed recolonization of newly available habitat, bringing previously separated populations back into contact. Over 2 million years, this pulse would have driven evolution at an accelerated pace, producing diversity and specialization at rates rarely seen in Earth's history. The great glacial epochs didn't destroy the dinosaurs of our alternative timeline. They changed them. They forced them to develop answers to issues that their forefathers had never encountered, to evolve bodies and habits that would have been unthinkable in the warm Cretaceous world where their ancestry originated. The 230 million years of dinosaur evolution culminated in the giants of the frozen world. Not the end of a story, but the latest chapter in an ongoing saga. The current interglacial then started. The ice retreated, temperatures rose, forest and tundra replaced the colossal steppe. And the world that emerged, the world of the present day, would have been shaped by 66 million years of history that never happened in our timeline. A world where dinosaurs still rule. Stand on a hilltop in our alternative present and look out across the landscape. The geography is familiar. The same mountains, the same rivers, the same coastlines that you would recognize from our world. Continental drift operates on timescales of millions of years, and 66 million years isn't enough to rearrange the continents significantly. Africa still presses against Europe, creating the Mediterranean. The Himalayas were raised by a long-ago collision between India and Asia. The Americas stretch from pole to pole, connected by the narrow isthmus of Central America. Although the animals on the map are entirely different, it is the same map you studied in school. Let's take a tour of this alternative: Earth, continent by continent, ecosystem by ecosystem. Let's examine the results of 230 million years of continuous dinosaur evolution. In our timeline, the highest concentration of large mammals on Earth is found in Africa, specifically on the savannas of East Africa. Our alternate timeline also includes the geography that gave rise to the Serengeti, the same grasslands that stretch to the horizon, the same seasonal rainfall patterns, the same volcanic soils, herds of ceratopsians with their horned heads bobbing as they graze, and bodies covered in sparse feathery integument, adapted to the tropical heat, would be seen in place of wildebeest and zebra. The megaherbivore niche would be filled by some enormous species, such as elephants. Others would be quicker, smaller, and live in larger herds that depend on numbers and alertness for defense. The predators would be familiar in function, if not in form. In order to find the weak, the young, and the lonely, packs of medium-sized theropods, descended from the Tyrannosaurus or Dromaeosaurid lineages, would patrol the boundaries of the herds. Millions of years of coevolution with their prey would have refined their sophisticated hunting techniques. Like African wild dogs, some would be pursuit hunters, sprinting kilometers to reach their prey. Others would be ambush predators, lying in wait in the tall grass, striking with explosive speed when prey wandered too close. Instead of the giants of the Cretaceous, the skies above the savanna would be teeming with smaller species of pterosaurs that have adapted to the modern world, taking the place of eagles and vultures in our timeline. Some would be scavengers, circling above kills and descending to clean the bones. Others would be active hunters, diving on small prey with the precision of falcons. And birds would be there too, of course. The one dinosaur lineage that survived the real extinction, now sharing the sky with their pterosaur cousins in a world where both groups had the chance to diversify. Cross the Atlantic to South America, and you would find something different. For a large portion of the Cenozoic, South America was cut off from other continents. According to our timeline, this isolation gave rise to unusual hoofed mammals, giant ground sloths, terrifying birds, and unique fauna. In our alternative timeline, the isolation would have produced unique dinosaurs instead. It's possible that sauropods, an ancient body plan preserved in a continental refuge, would have survived here. Their long-necked forms, still browsing in the Amazon basin's forests. Tens of millions of years of independent evolution might have produced completely new dinosaur lineages, forms unlike anything found on other continents. Even stranger would be Australia. According to our timeline, Australia's isolation gave rise to monotremes and marsupials, two mammals that developed separately from their placental relatives on other continents. According to our alternate timeline, Australia would have been cut off from Antarctica approximately 45 million years ago, along with any dinosaur fauna that may have existed at the time. Since then, those dinosaurs would have developed in total isolation, giving rise to creatures as distinctive and surprising to us as the platypus and kangaroo. Without knowing exactly what dinosaurs were present at the moment of separation, we can't say what Australian dinosaurs would look like, only that they would be different from dinosaurs anywhere else on Earth. The northern continents, Eurasia and North America, would be dominated by the grassland fauna we've been tracing throughout this documentary. Ceratopsians and hadrosaurs grazing in vast herds, tyrannosaurs and dromaeosaurids hunting in coordinated packs, troodontids using tools and living in complex social groups. The fauna would vary with latitude and climate. Tropical forests in the south, giving way to temperate woodlands, then grasslands, then tundra in the far north. But the basic cast of characters would be recognizable across the entire supercontinent. The oceans would be the realm of the marine reptiles. With hundreds of species by now, mosasaurs and plesiosaurs would occupy every marine niche, from open waters to coastal waters. Some would be tiny, nimble fish eaters that dart through coral reefs and kelp forests. Others would be enormous filter feeders that, like baleen whales in our timeline, cruise the productive polar waters with their mouths open, straining krill and small fish from the sea. The largest may be as big as a blue whale. The largest animals in history, measuring 30 meters in length and weighing 150 tons, were supported by the buoyancy of the water, which would crush them if they ever came ashore. What you would not see anywhere on this alternative Earth is a human. No farms, no fences, no cities on the horizon, no roads slicing through the grasslands, no ships on the seas or airplanes in the skies, and no domesticated animals obeying human commands. The world would be wild, in a way that our world hasn't been wild for 10,000 years. Perhaps because humans were altering ecosystems through fire and hunting, even before agriculture, our world was never truly wild. The way the planet functioned would be completely altered by this absence. Without humans to hunt them, the megafauna would be far more abundant than in our timeline. There may be tens of millions of ceratopsian herds in Africa, and their combined biomass is greater than anything we have ever seen in the mammalian world. Ecosystems would be continuous across entire continents if humans didn't fragment habitats, enabling gene flow and migration on a scale that isn't feasible in our developed world. The planet would have more biodiversity if humans had not driven species extinct. This is not just because dinosaurs would still exist, but also because none of the cascading extinctions that humans caused throughout our timeline would have occurred. Additionally, the chemistry of the planet would be altered. No fossil fuels burned, no carbon dioxide pumped into the atmosphere, no global warming threatening to destabilize the climate. The alternative Earth of 2026 would still be in the grip of the Pleistocene, the Great Glacial Epoch cycle, heading toward another glacial maximum in a few thousand years. Its climate controlled by orbital mechanics and volcanic activity rather than industrial emissions. The dinosaurs would face that coming, the Great Glacial Epoch, the way they faced every previous one, through migration, adaptation, and the slow grind of natural selection. Looking at this world, you might ask, is it better than ours? Is a world ruled by dinosaurs somehow superior to a world ruled by humans? The question doesn't really have an answer. For whom is it better? The dinosaurs would presumably prefer their world, if they were capable of preference. Mammals who were never given the opportunity to rule may not agree. The planet is indifferent. It's just a ball of rock and water and air, indifferent to what kinds of organisms happen to be crawling across its surface. However, a world that has remained stable for 230 million years has merit. A world where no single species has reshaped the entire biosphere to suit its needs. A world where evolution proceeds at its natural pace, driven by climate and competition and chance, rather than the deliberate choices of a technological civilization. Such a world has a certain purity, even if no one is around to enjoy it. The dinosaurs didn't choose to rule the Earth. They simply evolved to fit the conditions they found, and then they kept evolving as those conditions changed. They withstood the great glacial epochs and greenhouse spikes, volcanic eruptions and asteroid impacts, the emergence of flowering plants and the expansion of grasslands. They were the ultimate generalists, the great survivors, the lineage that found a way to persist through everything the planet threw at them. In our timeline, a rock from space ended their reign. In our alternative timeline, nothing ever did. No one can argue that the world today is not theirs, as it has been for 230 million years. This entire documentary has been devoted to discussing dinosaurs, including what they might have evolved into, how they might have adapted, and what forms they might have taken to fill the gaps in the modern world. But there's a question we haven't addressed directly, a question that might have been nagging at you since the beginning. How did the mammals fare? In our timeline, mammals had a huge opportunity when the dinosaurs went extinct. For 150 million years, they had lived in the shadows, small, mostly nocturnal, relegated to ecological niches that dinosaurs didn't want or couldn't fill. Then the asteroid hit, the dinosaurs died, and suddenly the world was empty. From burrowing moles to soaring bats, from tiny shrews to giant whales, the mammals exploded into that void, diversifying into every niche that became available. They had taken over the planet within 10 million years of the extinction. That chance never materialized in our alternate timeline. The mammals stayed in the background while the dinosaurs persevered. However, shadows are not insignificant. Instead of going extinct, the mammals would have continued to exist as they had for the preceding 150 million years, small, reclusive, and successful in their own small ways. They would have diversified within those limitations over the course of 66 million years of ongoing evolution, occupying every niche that the dinosaurs were unable to. They would have owned the night. Despite their diversity, dinosaurs were most likely diurnal, active during the day and sleeping at night. According to the evidence, early mammals specifically developed their enhanced senses and endothermic physiology, metabolism, to take advantage of the nocturnal niche, hunting insects and dodging dinosaur predators in the dark. In our alternative timeline, that niche would have remained theirs. After sunset, the modern world's forests would come to life with tiny, furry creatures that lived their whole lives between dusk and dawn, hunting and foraging. The underground would belong to them too. Burrowing is a strategy that favors small bodies. The energy required to dig increases rapidly with size, and mammals had been burrowing since the Mesozoic. In our alternative timeline, an entire ecosystem might exist beneath the feet of the dinosaurs, networks of tunnels and chambers occupied by mammal species that rarely or never venture to the surface. These underground mammals may have developed amazing adaptations, such as diminished eyes or even total blindness, sensitive whiskers to feel their way through tunnels, or improved hearing to navigate in the dark. The dinosaurs walking above them would not be able to see them, and the rulers of the surface would never even be aware that they existed. The treetops would have offered another refuge. Small mammals can climb where large dinosaurs cannot, and the high canopy of a tropical forest might have been essentially dinosaur-free, a world of branches and leaves, accessible only to creatures light enough to walk on thin limbs. Here, in our alternative timeline, primate-like mammals might have evolved. Prehensile digits and forward-facing eyes adapted for life in the three-dimensional maze of the canopy. Although they wouldn't technically qualify as primates because that lineage may have evolved very differently, they would occupy comparable niches and possibly acquire comparable adaptations as a result of convergent evolution. Could intelligence have evolved among these shadowy mammals? It's possible, though perhaps unlikely. The pressures that drove the evolution of human intelligence were specific. The benefits of teamwork and tool use, life on the African savanna, and the necessity of finding food over vast areas. None of those pressures would have applied to small nocturnal mammals hiding from dinosaurs. They might have evolved intelligence comparable to modern raccoons or rats. Clever, adaptable, capable of solving problems. But the spark that created human-level consciousness might never have been struck. But here's an interesting twist. It is possible that the mammals succeeded in an area that the dinosaurs never quite mastered. The ocean in its entirety. In our timeline, whales and dolphins evolved from land-dwelling mammals that returned to the sea roughly 50 million years ago. They became the dominant, large predators and filter feeders of the modern ocean, filling niches that had been empty since the extinction of the marine reptiles. Perhaps not all of the plesiosaurs and mosasaurs would have occupied those niches in our alternate timeline. Due to their attachment to the surface, the mosasaurs and plesiosaurs were air breathers with limited diving depth and submersion duration, a mammal lineage that evolved for deep diving, developing the extreme breath-holding capacity and pressure tolerance that modern whales possess. Might have been able to exploit resources that the marine reptiles couldn't reach. It's possible that mammals now inhabit the deep sea, that enormous area of darkness beneath the sunlit surface. Imagine an endothermic physiology mammal in the shadowy waters of the alternate present that is descended from a small ancestor that migrated to the sea when dinosaurs still dominated the land. It's the size of a dolphin, perhaps, streamlined for swimming. Its limbs transformed into flippers, its body insulated by a thick layer of blubber. It uses echolocation to locate prey in complete darkness while hunting in the deep scattering layer, a zone of concentrated life hundreds of meters below the surface. It can dive for up to 30 minutes on a single breath. Mosasaurs patrol the sunlit waters above it. However, the mammal is by itself, down here in the darkness and cold, ruling a domain that the reptiles never learned to take advantage of. Naturally, this is conjecture. The point is that mammals would have evolved something if dinosaurs had survived, even though we cannot know what those mammals would have evolved. Life finds a way, as the saying goes, not through some mystical force, but through the simple mathematics of variation and selection. Any niche that exists will eventually be filled by something. Mammals would have diversified to take advantage of niches that the dinosaurs were unable to fill. The Earth would not have been theirs. That prize would have remained with the dinosaurs as it had for 230 million years. But they would have persisted, adapted, survived. As a parallel dynasty, they would have flourished in all the areas that the reptilian rulers ignored, becoming lords of the shadows and masters of the margins. The mammals never went extinct in our alternative timeline. They just never got their chance to shine. And maybe they're still waiting in the deep oceans and shadowy forests of that other Earth. This is an odd idea to consider. The asteroid struck if you are listening to this, hearing these words, and comprehending them. This entire thought experiment revolves around that paradox. The very act of imagining a world where dinosaurs survived requires a mind capable of imagination. And that mind, your mind, exists only because the dinosaurs died. Human intelligence is not some inevitable endpoint of evolution, some destination that life was always heading toward. It's an accident, a contingency, the unlikely outcome of a very particular series of events that started 66 million years ago when a rock from space struck the Yucatan Peninsula. No one would be left wondering what might have happened if the asteroid had missed. This is not to argue that our alternate timeline could not have seen the evolution of intelligence. We've talked about the troodontids, large-brained theropods that may have evolved cognitive skills similar to those of dolphins or crows today. We've speculated about the social hunters of the Miocene, the pack-dwelling predators that might have evolved increasingly sophisticated communication and cooperation. Somewhere in the dinosaur family tree, intelligence of some sort would have most likely emerged. It's too useful an adaptation not to evolve when conditions favor it. However, intelligence such as ours, consciousness capable of reflecting on its own existence, pondering the nature of reality, and experiencing awe at the vastness of the universe is something quite different. A very specific set of circumstances led to the emergence of human consciousness. Primates were our ancestors. Over tens of millions of years, they developed sophisticated social structures, dexterous hands, and brains designed to navigate three-dimensional environments. They were then compelled by climate change to leave the forests and relocate to the African savanna, where they encountered new selection pressures that favored collaboration, communication, and future planning skills. Due to a feedback loop between social complexity and cognitive ability that appears to have happened nowhere else in the history of life on Earth, our brains underwent a dramatic expansion in a matter of millions of years. That journey was contingent at every turn. The outcome might have been entirely different if the primates had never made it to Africa, if the climate hadn't changed when it did, or if our ancestors had somehow adapted to the savanna. Intelligence might have evolved, but not the kind of intelligence that builds telescopes and writes documentaries and wonders about alternative histories. In our alternative timeline, none of those contingencies would have played out the same way. The primates might not have existed at all, or might have remained small tree dwellers, never descending to the ground. It's possible that dinosaurs dominated the savanna, leaving no ecological room for an ape to emerge and adapt new survival techniques. There wouldn't be anyone to ask the question you are asking now, because the particular set of forces that created human consciousness would never have come together. What if things had been different? But here's the thing, and this is the thought I want to leave you with. The alternative world is not inferior because it lacks human-style intelligence. It doesn't make it less significant, worse, or emptier. It's unique because of it. Furthermore, being different does not equate to being inferior. Throughout this documentary, we have been picturing an alternate Earth that is incredibly complex and beautiful. Ceratopsid herds traverse grasslands like living rivers, feathered predator packs that hunt with intelligence and coordination, marine reptiles cruising through oceans that have never known a fishing net or an oil spill, pterosaurs soaring on thermal currents above mountains that have never been climbed. Life in all its variety, hardship, and unlikely perseverance, all taking place on a stage that hasn't changed much in 230 million years. That world would not need us to appreciate it. It would have meaning without the need for a conscious observer. It would simply be, as our world simply is, a planet covered with living things, each one the product of billions of years of evolution, each one perfectly adapted to its niche, each one part of an interconnected web of relationships, more complex than any mind could fully comprehend. Since the first cell split in some ancient ocean, life has been aiming for consciousness, which we often consider to be the pinnacle of evolution. However, that is our prejudice speaking, the innate propensity of any thinking being to believe that thinking is the most important thing. Evolution doesn't have a point. It doesn't have a goal. It's simply a process. Variation, selection, inheritance, playing out over deep time, producing whatever forms happen to survive and reproduce. in whatever conditions happen to exist. Because they dominated the planet for 165 million years and left behind descendants that still fill the skies today, dinosaurs were spectacular, unprecedented successes rather than failures, because they did not evolve intelligence on par with humans. If they had survived the asteroid, they would have continued to be successes, adapting to whatever challenges the planet threw at them, diversifying into whatever niches became available, living and dying and evolving without ever once wondering why. And maybe there's something to be said for that, for a world that simply exists without the burden of consciousness, without the weight of meaning, without the endless human need to understand and explain and justify, a world where life just lives without asking what it's all for. The asteroid hit, the dinosaurs died, and here you are, 66 million years later, listening to a story about a world that never was. The warm darkness of a Mesozoic night, the sounds of animals moving through the forest, the stars wheeling overhead, the same stars that shine in our sky, the moon, the slow dance of the cosmos that doesn't care what walks below it. All of these things might be imaginable as you drift towards sleep. Something is also sleeping in that world. Some dinosaur descendant, curled up in its nest, watching over its herd, or drifting in the deep ocean's dark depths, its eyes closed, its breathing slowing, its mind, whatever mind it has, diminishing toward rest. The same night falls over two timelines and two worlds. The dinosaurs never questioned the reasons behind their existence, the asteroid that could have killed them, or the different possible outcomes. They are alive. The asteroid didn't just kill the dinosaurs, it paved a road for us. In this world where the rock mist, the air is thick with the calls of feathered sovereigns, and the earth shakes under the weight of titans that never knew extinction. We are the ghosts of a timeline that shouldn't have been. If you found this journey through the world that stayed green fascinating, hit the like button and let me know. Would you prefer our world or the one where dragons still rule?